All right. So in 18b, what we're going to do is have a look at this idea of rates of change, or link, start to link gradient and differentiation into kinematics a little bit. Our learning intention is to understand the difference between instantaneous and average rates of change. We also want to develop skills for calculating rates of change using the derivative function. So rather than just being able to rely on our gradient y2 minus y1 over x2 minus x1 as our only way of calculating average rate of change, we want to develop strategies for using the derivative. And hopefully, to measure your success, you can calculate both instantaneous and average rates of change. So, let's have a look at the content here. Well, we don't have too much more new calculus to introduce, so let's just define our two, average and instantaneous rates of change. You would have dealt with average rates of change before. And as you can see, the formula is quite familiar. Finding a rate of change over an interval, the gradient formula for two endpoints is used. So to link in with terminology that you've used before, we could say that m is equal to y2 minus y1, or our endpoints of the interval, the range endpoints of the interval, divided by x2 minus x1. Okay, well, what about in the terms of functions and not just points? Well, let's use our function notation here and say, well, then this second y value can be determined by substituting in the second x value into the function. So f of x2 take away f of x1 over x2 minus x1. All right, so if that's our formula for obtaining our average rate of change, then let's look at instantaneous rate of change. Instantaneous rate of change is finding a rate of change at a certain point. Use the derivative to find the rate of change at a particular point. So for example, at point A, to find the instantaneous rate of change at point A, find the derivative, and then sub in point A. So hopefully none of that's new. We have actually been already evaluating the gradient at a point. We just haven't put it in the context of instantaneous rate of change. So that's our link today. All right. Example 18b.1. For the function f of x squared equals x squared plus 2x, find A, the average rate of change for the interval x is between 2 and 3. Okay. Well, we could use our formula for gradient, or average rate of change, to find the function at the highest or the second x value, which is 3. Take away the value of the function at the first x value, 2, and divide it by 3 minus 2. So I'm using this formula here. Well, the function is x squared plus 2x, so let's evaluate x equals 3 into this formula. So 3 squared plus 2 times 3. 3 squared plus 2 times 3. And then from that we're going to subtract 2 squared plus 2 times 2. And all of that is going to be divided by 7.
No,
1.
Unless what about 1? I'm talking about the answer.
Okay. So
I'll talk about it, mouse.
15 minus 8 over 1, so there's 15 minus 8, which is 7. So in other words, we don't have any units for this particular example. We don't have any context. We just have a number 7, that the average rate of change is 7. So that for every unit that the x values increase by 1, the y values increase by 7, or did over that particular interval. Let's look at the instantaneous rate of change when x equals 2. For this, we want to use our derivative function and then substitute in the x value that we want to find the derivative at that particular point, or x equals 2. So the function, let's just write it down again, f of x equals x squared plus 2x. If that's our function, then our gradient function is, can someone help me out? 2x plus 2. So the instantaneous rate of change at x equals 2 is 2 times 2 plus 2, 6. Alright, let's look at the second example. And in the second example, we do have a bit more context. I think we probably should have put units on the volume, but we still have a bit more context. Okay. For V equals 600, subtract 10t, subtract 1 over 100t squared, for t is greater than 0, where t is time and v is volume in a balloon. A, find the rate of change after 10 seconds. And B, for how long could the model be valid? So, let's just say, to just complete the context here, that we have the V is volume in terms of, let's just say litres, and our T is time, whatever given it to us here, is seconds. So let's just it's kind of bad practice for us not to put that in there the first time. So I'm just outlining, I'm going to be talking in terms of litres and seconds. Alright, find the rate of change after 10 seconds. So are we trying to find here the instantaneous or the average rate of change?
Average.
Instantaneous? 50-50? Why? Why are we finding instantaneous and not average? It says find the rate of change after 10 seconds. Doesn't that mean? Can anybody pull apart this terminology?
Well, it's saying after 10 seconds instead of over the 10 seconds.
Exactly. So that would be the key distinction. If you saw the word over, it's talking about an interval. After is kind of like exactly after 10 seconds or at that point. So we'll first of all identify that we're looking at instantaneous rate of change. So we need the derivative function, don't we, mate? Yep. So our derivative function for volume, or v dash of t, is equal to negative 10 minus 2 over 100 t, or just negative 10 minus 1 over 50 t, or t over 50. Okay? So the time value that we're trying to find the instantaneous rate of change at is t equals 10. So we substitute in t equals 10 into our derivative function for v. Negative 10 minus 2, sorry, not 2, 1 over 50 multiplied by 2, or negative 10 and let's say 2/5. Okay. Now what units do we have on that? Well, I thought that was a hand going. It's a rate of change. So something's changing per something else.
I was going to say, why did you put 2 in?
Yeah.
Well, that's 2/5. You could put that. Pardon?
Be
In the
10
bracket.
Ah, it should be a 10. Yep. Sorry. 10 over 50. 2/5. Yep.
It hasn't given us a unit for the volume.
That's right, but we have
C slash seconds.
L for litres.
It doesn't help. I thought it was C for capacity.
All right, I'll write it out again. Okay, no need to get all funny about it. volume in litres.
I wasn't trying to be
So what would our rate of change be now?
negative 10 and 2/5 liters per second.
Excellent. So litres per second. So what that actually means is that every second the balloon is losing 10, at 10 seconds, it's losing 10 and 2/5 litres per second. That's how much is shooting out of the balloon at that particular point in time.
Big balloon.
Great, huge balloon. Maybe it wasn't litres. Or maybe we're talking about a hot air balloon.
Isn't 10 over 50 150?
10 times 150. 10 times. Yes. We got it wrong the first time.
Until I was like,
No. Yeah,
It's not your days,
that's all right. We're getting there. Small addition. Thank you. Second hand up over there.
I'll add the same comment.
All right.
Yeah, but I already did.
Good. All right. So, for how long would will the model be valid? So, for this volume model here, what is the assumption? What are we assuming about that the volume will always be?
It'll always be above 0.
It will always be above 0. So, we could assume that the volume is always above 0. So, for this quadratic, if we find the x-intercepts, then that's going to give us a time period, is it not?
oh, you just have to say
All right. Now, I'm not going to bring up the CAS, but if we were just substituting this 0 equals and then this, so let's just say we use CAS to solve 0 equals 600 minus 10t minus 1 over 100 t squared. Then the two values that we get are t equals negative 1056.78 and t equals 56.78.
You have to discard the negative.
So we're going to discard the negative, so we're not going to go backwards in time. So we can say, therefore, the model is suitable. I'm using the same language that they use. They said, when is the model suitable? The model is suitable for time where time is between 0 and 56.78 seconds. What happens at 56.78 seconds? The volume is just above 0. That's right. Okay. So, hopefully the two things you want to take away is the difference between average and instantaneous rate of change, and secondly, how to be able to calculate instantaneous rate of change from the derivative function. Thank you.